Okay, so let's look at some long-term projections. Yes, there is a cyclone in the Bay of Bengal and it's raining in Mumbai very nicely all day, almost in December 1st. So that's fantastic. So I went out in the rain and just came back and decided to record a podcast before taking a shower. Okay, so here are some long-term projected future in the perspective of past changes that have occurred in atmospheric CO2, surface temperature, and sea level. We are looking here at the reconstructed temperatures from 21,000 years ago when we were in the peak of the last glacial, it's called the last glacial maximum, and then it started to decline and started to go away by 18,000 years ago, and with a few hiccups it was done by about 11,000 years ago or so. So you can see that compared to the present temperatures, change was pretty massive, cooler by 12 degrees centigrade or higher, and you can still see the polar amplification here as well. So polar amplification is a feature that occurs in cold climates and in warm climates. So projected RCP 8.5 scenarios for 2100 show also the polar amplifications and the various patterns that we have talked about. So the CO2 projections starting with 20,000 years ago in the glacial level of 200 ppm. We reached today, this is already a few years old, so you were 300 something, and the projected assumed levels of CO2 are here given as 1280, 2560, 3840, and 5120, and how long they would take to ramp down. So you are looking at future times here. Sorry, let me make sure that center and bottom changes in CO2, global surface temperature, and sea level from paleo data and model projections. Intermediate complexity models were used for future projections, assuming a total of 1280, 2560, 3840, and 5120 petagrams carbon emissions. So those are not ppms, but those are the amount of emissions assumed in the intermediate complexity models, because they can be run for a long time very easily, as opposed to coupled climate models, which are not so easy to run for such a long time. With shading indicating uncertainty, red squares indicate the results from years 2100. So that's where you would end up with if you reached those kind of emissions. And 2300 for the RCP 8.5 scenario for comparison, which is up here. And yes, okay. Vertical gray bars show the range of uncertainty based on a range of climate sensitivity from 1.5 to 4.5 degrees centigrade. So we talked about climate sensitivity, and the warming you would end up with obviously depends on the climate sensitivity. The intermediate complexity models do not explicitly do the whole climate, so they have ways of assuming sensitivities to project into the future, far into the future. So here is the Anthropocene 2100 RCP 8.5, and then the various levels of CO2 emissions that I just mentioned, and what kind of warming you would end up with the different sensitivities. As I said before, the intermediate complexity models are already quite simple, and what to do with such long time projections is not always very clear, but it gives you a sense of where we are compared to the recent past, starting from the end of Pleistocene into Holocene, where we are today and where we could end up depending on the emissions, plus how long it would take for things to come back to normal, and what would happen to sea level. So sea level, because of all the glacier melt, has risen into the Holocene by almost 120 meters. Obviously, lots of glaciers were built on North America and Europe into Eurasia, several kilometers thick, and when that melted, you raised the sea levels quite substantially. And here where we are and where we could end up into the future, order 50 meters depending on the emissions. Okay, leave that there and come to regional climate change linear trends. In April 1st, snow water equivalent observed for the period of 1955 to 2016 in the western US. So you are looking here at California, Oregon, Seattle, into Canada and Alaska over there. So these are red circles indicate decreased snowpack and blue circles indicate increased snowpack. So 80% decrease or 80% increase. Obviously there is no 80% increase anywhere. There are few regions with order 20% to 30% increase, but the red circles are all over the place, which means over these decades, snowpack in terms of the snow water equivalent have significantly decreased up to 80%, and this region is climatologically dry, related to the climatologically cold East Pacific temperatures and coastal temperatures, but obviously some mountain regions and some parts of California and Washington do get plenty of snow and rain, but they are in extended droughts for almost a decade. Another example is from India, where the trend over the periods monsoon trend from 1950 to 2002 was negative. You can see this is millimeters per day per decade. So this region has experienced drying at least till 2002, and then there is some debate about whether the monsoon is recovering since then. And as we mentioned briefly before, if global warming was happening during this period, you would expect land to warm faster than the ocean because it has a low heat capacity, which would increase the thermal contrast between the land and the ocean, which would actually lead to increased rainfall from what we know. But one of the hypotheses we have is that aerosols during this period created solar dimming and prevented the land from warming as fast as it could if there were no aerosols. So the ocean in fact ended up warming more. Indian Ocean is warming rather uniquely because it is getting some heat from the Pacific through the Indonesian seas. It is getting some heat from the Southern Ocean through the meridional overturning circulation that we looked at when we looked at the circulations in the ocean. So that now is expected to have turned around. Is it because the aerosols have reduced? Not necessarily, but somehow the solar dimming may have gone away, or there may be other dynamics playing a role, and this trend is seriously positive compared to the negative here. So millimeters per day per decade is order 1 or greater over these regions. This again raises the question of whether we are still experiencing multi-decadal variability, and hence there is a recovery or there is a phase change of the multi-decadal variability. But that doesn't remove the global warming impact arguments, because global warming, as we said, would just load the dice, or it would modulate the natural variabilities at any time scale, like multi-decadal time scale. So one would have to be careful about whether this is a real recovery or whether it's just a temporary multi-decadal turnaround. And this also doesn't take away the argument that extreme events have increased and they have become more widespread over this region of India. So that still leaves us with lots of issues to deal with. The other thing to look at is the regionality of the trends in global chlorophyll over 1997 to 2019. Certainly a relatively short period, but this is the best data we have from chlorophyll. People from satellites, people have reconstructed longer time series by various methods, but I'm not going to show those. So you can see that there are regions where there is increase in percentage of chlorophyll in linear trends per year, percentage increase per year, so 3% or so here. But there are critical regions like the Indian region, which is warming, and there is significant drop in chlorophyll, which is consistent with the surface warming, stabilization or increased stratification, and difficulty with mixing nutrients into the light zone, as we mentioned before. And there are also decreases in chlorophyll over here in the cold tongue region and in the Atlantic. So these have to be looked at carefully. This is not the equator, but here. So we looked at the sea surface temperatures trends and said it is not warming as fast as the west, or it may even be cooling, but then why is chlorophyll not increasing? So these sorts of questions have to be answered, even though chlorophyll is showing some increase here well to the south of the equator. So of course there is also increase in the Southern Ocean, but there are indications of other ecosystem perturbations over here as well. So regional trends here are very important because biology is very much a regional response, and that also goes for land vegetation, terrestrial ecosystems. So looking at the US northwest into Canada, we are again looking at various ecosystems like tundra, conifer forest, cool mixed forest, deciduous forest, warm mixed forest, woodland and savannas, shrublands, woodlands, and grasslands. And these are projected changes in vegetation, center row with the legend here, and fire frequency shown here. Vegetation is shown for years 1971 to 2000 in the left here, 2036 to 2065 here, and 2071 to 2100 here. Fire frequency in years is shown for the 20th century here and the 21st century here. So you can see the changes that are shown. So the increase in frequency in the range of 1 to maybe 50% or so changes from here to here. Okay, so one has to be careful about the frequencies. As we said before, this story is without any fire suppression effort, so there are certain assumptions made here. Plus it's always a matter of whether it's the area of the fires, number of fires, intensity of the fires, and so on. So fire modeling has its own uncertainties as well. So let me leave that with a brief introduction to regional trends. There are many more details. We looked at the very first opening in this chapter was the CMIP 5 map showing physical systems, biological systems, and human and managed systems, and we showed that each region of the planet is affected to various levels, which are all regional. So regional can go down to state levels, parts of a continent like North America, country like India, and so on and so forth. And there are lots of new regional assessments being done by various countries as well, including India, China, and so on. Okay.